Okay, so again, for those who know me, I'm Dennis Hanisak here at Harbor Branch. I've been here for quite a while, most of my career you might say. My interest has always been on better understanding nature, better understanding the environment. In particular, I always like to say I'm the plant guy. I study algae, primarily macroscopic algae and seagrasses. And I want to tell you really kind of a lead-in to our speaker, tell you a little bit more about our network. So this is part of something we call the Indian River Lagoon Observatory. It's an environmental observatory, and just like I said, I'm interested in nature and trying to better understand it. My particular group, this more broadly, is interested in the Indian River Lagoon and better understanding how it works, and hopefully with the idea that ultimately leads to better management. And I will always argue that we have to understand how the system works and how we would like it to be. And there's a lot of things we can do about that on the management side. There's three key parts to this. One is long-term ecosystem research. There's a lot of folks that are involved with that at Harbor Branch, not just myself. You probably know about some of our marine mammal work. You know about Brian Lapointe, who'll be here this afternoon as well as here this afternoon. Some of his research. We have a large number of people that are doing work in the lagoon, and there's a whole bunch of other organizations. And so the second point is that one of the goals of IRLO, the acronym, is really broader cooperation. Many of you know about the Indian River Lagoon Symposium. That's just one example. So, you know, the last 5 years for one day, we get all the people that are interested in talking about the technical side of the science and the research. We all get together and we spend the day updating each other and talking about future plans and so on. A third important piece is really what the focus is today and the focus of our network, and that's a network of advanced observing stations. Before I talk about that, I do want to say in terms of collaboration, we have a very recent product. Besides myself, some of the people in the room were instrumental in doing a workshop here in December, which was entitled Connecting Users to IRL Data, because we recognize in the scientific community, but I also think the management, I think the political community, there's a lot of data out there. Sometimes it's hard to get, sometimes it's hard to understand. We need to do a better job of making it available. We need to do a better job of visualizing it and translating it to all kinds of users. So just like the students from Pine Jock, or whether you're a manager or whether you're a scientist, there's different types of people, but we may all be interested in the data. We may want different products. And so we had a very diverse steering committee. I'm not going to spend much time on this. I just gave a presentation last week to the NEP about it. And we also had an online regional survey. If you're interested, you can go online to our website. There's some hard copies here. We've printed them. If you're interested, that's a quick summary. I'm not going to go through it. That's what the report is about. I want to call your attention to it and to say that this is really tied in heavily to monitoring because that's a really important set of data. So if you haven't heard about that, please look into it. So what is IRLON? The Indian River Lagoon Observatory Network of Environmental Sensors. It's basically consistent with what I said about IRLO and our interest. We're really interested in long-term observations of, in this case, water quality. Key parts is real time. Nowadays, we want everything right away, right? Real time. This is very close to real time. We also have a high requirement for accuracy. We don't want to make decisions if the data aren't right? So we spend quite a lot of effort on that, and high resolution. So lots of sampling at key locations. And a key part of this is what our speaker is going to focus on today, which are LOBOs. And you read about LOBOs in the newspaper a lot. LOBOs is an acronym for Land, Ocean, Biogeochemical Observatories. It was developed initially by scientists at MOBARI, Monterey Bay Aquarium Research Institute, with NSF funding. And it is available. It is something you can buy, quote, off the shelf, although there aren't that many of them. So I still think it's still a developing product, as is all technology, right? The phones that most of us have are still being modified every year, right? Same is true for the instrumentation. So what do these instruments measure? A suite of important parameters in the environment. some of the things that we all try to measure routinely and can do pretty easily, like temperature and salinity and dissolved oxygen, but also things, again, I'm a plant guy, so I think about things that reduce seagrass growth, and those are particles in the water, or turbidity, or watercolor, that brown discoloration that we see, which is due to decaying organic matter, and chlorophyll A, which is algal pigment, so it can be blooms, but it can just be regular background populations of phytoplankton. The most exciting thing to me always was being able to do real-time nutrients. I couldn't, I really was very skeptical about this. I had done this for years manually, slaved over it. That exact same technology or method basically has been miniaturized to such a way for the phosphate analysis it takes 20 minutes, and that's why it's not exact. It takes 20 minutes to get the data posted because of phosphate. And the idea that we have sensors that can beam light through a little piece of water and come back with a good estimate of nitrate, which is present in very small quantities, it's kind of always amazing. So this really is cutting edge technology, and we did go with it thinking that it could do the job and it had the track record. People always want to know what's really in a LOBO. Well, I'm not going to go to it in great detail, but this is some of the instrumentation. There's a brain, a data logger called the Storex. Most of those sensors I talked about are on this WQMX up here. So on one end we have oxygen, we have temperature, we have depth. On the other hand, we have those optical sensors that do chlorophyll and color and turbidity. This is what I call chemistry in the can. That's where the phosphate's done. That's that miniaturized little phosphate procedure that I talked about. Can't quite see the SUNA, but that also is an optical sensor in the background. Here you can see them when they're brand new. This was our first one, the first day we were putting it out. You'll see everything has been taped and coated with anti-fouling tape. Some of the cables you'll see are covered with copper. All this is because anti-fouling. That is by far and away the enormous challenge that we have when we try to put sensors into place like the Indian River Lagoon, which probably has the highest fouling rate of any place that these instruments are deployed. We can communicate with it. Basically, a cell phone call comes in to a server every hour from the antenna. This is actually a weather station, so we get the classical weather station parameters, precipitation, temperature, wind speed, and so on. It's powered by a solar cell. A lot of times people say, what's going to happen in a hurricane? Isn't that going to get blown away? Well, it might. But it has enough battery power, probably for a good 2 or 3 days. So even if we were to lose that capability, we would have incredibly valuable data during these rare but very important episodic events. As I said, you can go real-time online. Here it is. This is what the homepage looks like. And most importantly, if you're interested in data mining, and anybody can do this, there's no registration process or anything, you want to go up here to LoboViz and explore it. And we're happy to work with you on how to do that. So a few years ago when Harbor Branch was doing a new strategic plan, IRLO was kind of just something that was just starting. And Harbor Branch made the investment to buy 2 LOBOs, which we deployed initially in our canal right out here, channel right out here, and at the end of Harbor Branch. This is behind the Johnson House, which is here on campus. Historically, the area's been called Linkport. It's probably the single most studied place anywhere in the lagoon because of its proximity to Harbor Branch. A lot of long-term studies. The district has monitoring stations there. We have long-term monitoring stations and so on. And this is this part of the lagoon is incredible in terms of its diversity still. Southern Indian River County and northern St. Lucie County, as you probably know, have not been hit by a lot of the same crises that we've had to the north and south just this year. This is what a typical installation looked. Then if you're here, Ben Metzger, key to one of our engineers designing this, and I kind of described it a little bit, but we basically put these on pilings or markers. And how do we figure out where to put them? Well, 2 years ago, actually it would be on Friday, it'll be exactly 2 years ago, we had a meeting here at Harbor Branch. We formed a group of people on the technical side up and down the lagoon. We called it the Science, Technology, and Advisory Committee. And we met and we basically said, here's what we're thinking. And they actually said, well, here's some better ideas too. And we went with what they recommended. Key to this was focusing on the issue of freshwater discharges, okay? Whether they be in Lake Okeechobee, which is episodic, happens every few years when it rains a lot, right? and we'll talk about that more later. But also just the canals that are there all the time, such as the ones in Indian River County. And also we realize the importance of the inlets, so that exchange of freshwater and saltwater, to me, is really important to understanding the lagoon. And that's why we picked these stations. And again, this is just some pictures. You can see I made some presentations, but you'll see most of the time I was writing down what everybody said and trying to follow it as best I could. A key part of this was we had folks from Sanibel Captiva Conservation Foundation, which is over on the west coast of Florida. In particular, Eric Milbrand is the lead there. They were part of our workshop. But prior to this, after we had made the decision to go with LOBOs, Brian, I, and a technician went over there, and they were gracious hosts to us. We spent 2 days there. Half day we went behind the scenes. They told us about all of their problems, fouling, this, that, and the other thing. Showed us the toolkits, showed us everything that they did. And then the next day we went out with them and did one of their sites, just a regular maintenance day, just to get an idea of what came out of that. So we learned a lot. I learned a lot. And I saw some of the challenges. Some of the things that we did differently, for example, was they have to put a diver in the water to change out their LOBOs. I came back and I talked to Ben and some of the engineers and say, I don't want to put a person in the water. Can the engineering team, can you design us another way to do that? And we do. We have a way with a pulley system to deploy the instruments, and it's quite nice. So here's their site. It is, we're now the biggest site of instrumentation with using LOBOs there is. It was Sanibel. We're very close. They're studying the other side of Florida. They're studying the Caloosahatchee system. All of the issues we have here, they have. Okay? They actually get more water. It's a different system, though, too. They actually have need for a freshwater part of the Caloosahatchee system. So freshwater macrophytes are really important in that system. So that's a very challenging place to try to manage as well. So that's just a couple of pictures showing you that, yes, Brian and I really did go out on a boat together. And this is where you can see they were showing us their procedures and discussing the fouling. And again, it was an invaluable experience. And we learned a lot from it, and they were very helpful to us. So this is now our network. We have 10 locations. And we started off, as I said, with one right here at Harbor Branch. And then early on, our foundation, the Harbor Branch Oceanographic Institute Foundation, invited us to submit a proposal. And I think at the time they were very interested, and again we had the strategic plan process going on, working with the community and finding out, you know, well, what we could do to tie us more closely to some of the needs that the community has. And the Indian River Lagoon is a major concern. And at that time we had already had the blooms to the north that happened in 2011, unprecedented, unlike what happens at Lake Okeechobee. And in 2012 we followed that with a brown tide. So with those funds, we were able to put a new site in at Fort Pierce, just north of the inlet, near where there's a freshwater outfall, Taylor Creek. We put one at the south end of Vero Beach, where those 3 main relief canals drain. All that water flows south. That's where I had been studying for a number of years using other techniques. We also put one near the Sebastian River, which comes out here, and the Sebastian Inlet. So that's our Sebastian site. So again, very consistent with the STAC recommended. These areas are very dynamic exchange of water and water quality. So the first one went online in 2013. The others went in online from the foundation funds the end of 2014 and 2015. And I kind of call that the northern network. The southern network was funded primarily by funds from a legislative request. This is, a lot of you know, the Negron panel that came together and recommended substantial funding, and this all has to do with what happened in 2013 with the discharges from Lake Okeechobee. And that's also Orca, I know, is here. I saw Edie, and they also got their funding in the same actual line item. Our locations here are strategically placed at the base of the South Fork, the base of the North Fork. Lake Okeechobee water, when it comes in to the south, C-44. And then these 2 arms of the estuary come together. This is the Stewart Bridge, the Roosevelt Bridge in Stewart. This area we call the mid-estuary. And so this site basically takes in consideration the blending of these 2 parts of the estuary. The water then flows out and out to the Indian River Lagoon. And we have one in the Crossroads area, which is a very dynamic area. And I'm glad to see Dr. Ned Smith in the room because he and also I know people from the Water Management District, South Florida, have both figured out that about 91% of all the water that comes out here goes immediately or fairly immediately out the inlet. That inlet is really, really important. Many years ago, Grant Gilmore identified this as the hotspot of biodiversity overall in the lagoon. And also, many of you know this is the northern extent of the Florida Reef Tract. And I see Dr. Voss in the room, and he has a really nice program that is looking at this area here, including the black water or discharge events and how that might impact coral health. We also, and this was a STAC recommendation, to put a site in Jensen Beach, because the question was, even though most of the water flows this way, we do know that some water flows there, and even if it's a smaller fraction, what is the water quality impact? And a lot of these are areas of large interest in restoration. So I see Florida Oceanographic Society has some folks here. This is an area of great interest to them as well. And our very last site was actually a proposal that went in before the other proposals went in, but got funded after the other ones. It was actually through the Rivers Issues team, funded through the South Florida Water Management District. And that one just went in very recently, end of April. And this actually was something that the STAC had recommended to directly capture what comes down the C-44 canal from Okeechobee, Lake Okeechobee. So we can get a better idea of watershed in South Fork versus what comes in, from the lake. Benefits. This is really a quick summary. I really think this and some of the other efforts that are going on in Lagoon provide unprecedented opportunities for the environmental data, consistent with what we try to do with the observatory. It's real time. Anybody can get it, anytime, wherever you are. It allows us to follow environmental changes, and I also mentioned the Sanibel infrastructure they have as well, very similar to ours. So we can do comparative coast. So someday when that major storm does come up, and Lake Okeechobee does get a really high amount of water, and the whole center of the state has a serious issue with water, what is going to be the impact? But what's the baseline? What happens in a dry year on both coasts? What happens in a wet year? That long-term variability is so important. We think this will be very helpful to managers to make the proper decisions, informed decisions. Great opportunity for modelers. We'll probably talk a little bit about that later. And even as I referenced to the Pine Jog folks, it's a tremendous platform for education and outreach activities. I use LOBO data in the graduate courses I teach. We use it in our high school courses that we teach. So kind of exciting to me also is that recently we redid our IRLO website. This is what it looks like. There's the link. Take a look at it. And particularly, we started something called IRL observations. After all, if you're an observatory, you should make observations, right? And these are more like blogs, and they're written by different folks. I've written several of them. Kristen Davis, who's been with me, has written a couple others. You'll see other members of our team. We've talked about things like biofouling, including some of the data patterns we've seen. And moving forward, I think this is the venue that we will use to try to rapidly communicate with everybody, with the public. So stay tuned. That's my contact information. I think most of you know how to find me. I can't stress the importance of having an awful lot of really, really good people who work with me. There's only 2 of them in the room today because the rest of them are out in the field working on the regular maintenance. I think I mentioned all of the funding sources already. I did not say the Save Our Seas plate, but that is what allows us to do a lot of the ongoing work that we do in the lagoon, including some of the LOBO work. So that is to get everybody kind of up to speed on where we are. It's something we had promised we would do when we had the STAC meeting a couple years ago, that about once a year we'd give an update, and it kind of just worked out on the schedule to do this. And I think that allows our speaker then to really focus on the data that he has been working on. Without further ado, Ian, thank you for coming.
Excellent. Yeah, I'm going to reiterate that right again. 3,000 miles away, I picked up the data and started working with it and called Brian and said, I don't really understand what's happening here. And we've carried it through to the invitation to come down here and speak to you. And if I can, so that was a great intro. We're going to reiterate some of this again. Mainly, you're seeing my thinking as I work my way through the data. But a lot of it was informed by talking with Brian and Dennis over the last couple of weeks. So think about that. This is data. The event happened in the last month. We're presenting the science now. So is it finished? No, it's not finished. But the ability to get live data, and any of you can get live data. That's why the URL is everywhere. You should get on there, look at your environment. It gives you a totally different perspective on what's happening around you. And for someone who's been in the field for a long time, we used to put moorings out and come back in 13 months to pick them up and hope that the instruments worked. Now we know they're working. Now when they're not working, we can go out, and Kristen can go out, and her team can go out and fix them and move on. So the quality of the data goes up. Our ability to link the data with what's happening immediately goes up. It's really a revolution. What we haven't gotten to, though, is incorporating that data regularly into our own lives and into the management of the resources around us. So some of that is going to come out in this talk, I hope. But for the most part, the key is we're really in a new era. And people like the students that just walked in, you're going to run with this. What you've got to do is a lot different from what we've got to do, but you're going to have a lot of fun doing it. Okay, let's see. All right, so about a month ago, is it a month now? It is a month. Started to get the stories and the pictures showing up in the media on the harmful algal bloom, the microcystis bloom coming up. What we're going to cover now within this talk is one, the sites, the IRLON sites. Then we'll talk about the biogeochemical data. That's my specialty. We're going to talk about the sources of the water within the estuary, and then the relationship between the sources of the water and the dynamics of the system, specifically looking at what triggers the harmful algal blooms, or at least our current thoughts on what's triggering the harmful algal blooms and what's generating the green mats in the surface of the water. So as Dennis said, the data is available on the website. It's great. You can download it. You can graph it within LOBO Viz. It's a pretty nice tool. Is it the tool that we want to get to? Probably not. It's a great step to go along the way. There's still a lot of work to be done. There's still a lot of opportunities to learn how to take this data, incorporate it into a better visualization tool, and get it out so that people understand it, and so we understand it ourselves. Here are the locations. These are the data sites that I'm going to concentrate on. The three around the bridges, the source from Lake Okeechobee, and the source from the sea. So this is the regional. Here's Lake Okeechobee, the S308 site, which releases water into the canal. The S60, is that 60? 80. And then the Atlantic Ocean. And then there's other sources of water from groundwater, of course, and surface water coming into the lagoon. And we'll take a look at that. This is where the sites are that we're going to look at, so a much smaller area, but the sources, of course, are much larger and relatively remote. All right, this is the discharge from the Lake Okeechobee monitored at the 308 site. And the data that we're going to talk about mainly encompasses June into July. You can see it was running at about 1,800 to, or 1,500 to 2,000 cubic feet per second. There's a little downturn here and a big downturn after the end of 4th of July, and we came right back up. So that's our discharge. This sets up the freshwater input from Lake Okeechobee. All right, we're going to look at two of the biogeochemical tracers that are relatively stable within the system. The first one is color dissolved organic matter that Dennis mentioned earlier. Its source is decayed organic matter. Coffee is an example of something that you're looking at, in which we take grounds, we put hot water over it, and we get colored liquid. That happens in nature. We end up with CDOM in the water. The second one is the salts in the ocean water, and that we measure through the salinity on the LOBO systems. So these we can use as conservative tracers and watch the different sources of water move through the system. All right, so now what I did was I took all the data from the sites and plotted on the salinity versus the CDOM. So here are two conservative tracers, and what we see then is we're going to look at different sources and mixing lines between them. So here's our seawater at this site, and it's about 35 PSU, practical salinity units. Lake Okeechobee water has very low salinity, but lots of CDOM. So our seawater has very little CDOM, lots of salinity. But what was interesting to me was we ended up with a big triangle, which means there's another source here other than just these two, and that is runoff and other freshwater sources. So this is relatively low in salinity, but not zero, and quite high in the CDOM. So I said, well, all right, so what's that coming from? Well, we go back and look at the data from these sites. January was a very wet January here, about 10 inches of rain relative to about 1 to 2 normal. And this is just the January data. So this previous slide, that's from January through May. Here's just January. And in just January, the sites pretty much just run between this source and this source. So this is just, along this line is the percentage of water. So right here would be 50% of the water is coming from runoff, and 50% of the water is coming from the ocean. Very little Lake Okeechobee input in this case. This is the situation June and July. Marked contrast to either of the previous two slides. We still have the ocean. We're not moving the ocean very much, no matter what we do. But now we're missing the runoff. And now we don't have a connection between the sites. There is no salinity run up all the way through. So here's our sites down here, Triple Point and SF2, and they're basically not seeing much of a signal from the ocean at all. So that has a lot of implications for the dynamics of the estuary, for everything within the estuary. One of the questions, of course, is the nutrient loading within the estuary, and what's that doing to productivity within the estuary, and in particular, in this case, to the growth of the harmful algal bloom. So when we plot the same data set, but in this case, we still have CDOM on the x-axis. Now we've got phosphate chemistry, or the micromolars of phosphate, on the vertical axis. Well, here's our seawater, remember. Very low in phosphate, and of course, very low in CDOM. Here's our Lake Okeechobee input as measured at SF2, the black circles. They're down at about 60 ppb CDOM, and phosphate's about 1 micromolar. Sorry. Here's our runoff axis. And now we've got our runoff up in the 5 to 7 micromolars of phosphate, and CDOM's running between 80 and 100 ppb. So a very distinct pattern here. Also notice that there's a couple of times in which the SF2 runs up along this mixing line to the runoff from the Lake Okeechobee up in the runoff. We'll get to that in later slides. But we end up with, of course, then very distinct end members in the phosphate CDOM space. So to put that all together, what we're looking at now is 3 sources. We have the ocean, which has high salinity, and we've got about 10 ppb of CDOM and less than 1 micromolar of phosphate. We've got the Lake Okeechobee as represented by the SF2. And again, we're taking all of this data not from the end members out at the sources. We're not looking at the ocean, and we're not looking at Lake Okeechobee. We're measuring it as they come into the system. So we've got less than 1 PSU salinity. We've got 60 ppb CDOM and about 1 micromolar of phosphate. The runoff, though, is dramatically different. We've got brackish water at about 10 PSU salinity, 100 ppb QSDE, and greater than 6 micromolar phosphate. All right, so the interesting thing about that, then, is I'm looking at this and trying to understand this, called up Brian, and he showed me a series of his of his work that had basically been saying this as we went. So he had a 2012 paper that presented data on precisely this, what we were looking at. The interesting thing about this is he collected the data in 2004 and 2005. So within an academic construct, it takes a long time to get from the data collection to the analysis to the peer review and out into the publication. Now here we just compressed pretty much the entire discussion to about a week or two. I think it was about a week after I started looking at it, then you and I had the conversation. And then he followed it up in a 2015 paper, and then this spring a report to the county on his. So this isn't necessarily new, but what it's giving us is a real quick look at the data from the where it's happening, when it's happening. All right, so now we'll look at the nutrient loading. Blooms tend to be driven by nutrients. Nutrients always end up being the limitation for the most part. But what plant growth needs sunlight, needs nutrients, needs time or stability. So if you don't have enough time, you're not going to see much of a bloom. If you don't have enough nutrients, nothing grows. And of course, no light, nothing grows. So when looking at, and as Dennis said, cool thing about the LOBO systems is that they have both phosphate and nitrate systems on this. So we get a much deeper look into the nutrient chemistry from the LOBOs. We're going to look at the red field ratios. The red field ratio is if you took a bunch of phytoplankton, you go out and you analyze it for the ratio of the molar ratio of the phosphate and the nitrate, you end up about 16 atoms of nitrogen for every atom of phosphate or phosphorus, which is generally as phosphate. So that's sort of our ratio that healthy plants, normal populations, always go to about 16 to 1 in that ratio. Blue-green algae tend to outcompete. They're the bloom material when phosphate is abundant. So when red field ratios are low relative to nitrate, so more phosphate than nitrate, then we seem to get more algae in the blue-green algae. Otherwise, we're going to see the eukaryotes, the diatoms, et cetera, move forward. So the next set of slides, what I did was I plotted the phosphate and the nitrate data from the LOBOs. This is June into July. And this is ratioed in the red field ratio. So there's a 16 to 1, 16 nitrate for every phosphate. And so when we see the phosphate above the nitrate line, then we're relatively enriched in phosphate. And when it's below, we're relatively enriched in nitrate. So this is the SF2 data. So before we looked at all the data plotted at all the sites. Now we're going to look at it in time, on time scale. So time gives us a chance to now look at what's happening on the daily dynamics. So we've got a tidal system in an estuary by definition, and then of course light comes on during the day. Plants grow during the day. So we're going to watch the cycles of the biogeochemistry from the LOBO data. So what we have here then is relatively low. One, we're pretty close to red field throughout the period, and relatively low, 1 to 2 micromolar of phosphate. Now that 1 to 2 micromolar of phosphate is still a fair amount of phosphate. This is plenty of nutrients in this system, but compared to other sources, this is relatively low. So we move further up into the estuary. Here's the South Fork data, and now we're seeing phosphate above, relatively enriched above the nitrate. We go to the North Fork, and we're significantly higher. So now we've got phosphate up into the 5s and 6s, and a very distinct tidal pattern, and the nitrate is relatively low. Again, relatively low only in relationship to the red field. Now you'll see spikes here in the nitrate data. I really didn't do any QC on this data set. We just took the data as it was out there, so there is going to be some data probably removed later after we go through your QA/QC processes and its final data. At this point, it's all preliminary data, so you have to take that in that spirit. Okay, we go further along to the middle estuary, and it's not quite as enriched as in the North Fork. Now we get out closer to the ocean, and we're seeing much lower as we would expect from the oceanic input, some tidal input here, freshwater signal in up until about 27th of June. Okay. So we saw some curious spikes in the South Fork LOBO data. And remember, we talked about looking at all of the data and looking at our end members. We had negative relationships between salinity and phosphate and positive relationships between, I'm probably getting myself confused on that one. We will let the slides figure it out for us. So here's our spike. So now we're looking at the phosphate and the salinity, and the ocean, where the source of the salinity has very low phosphate. And in this data, we're seeing very positive correlations as these spikes move through between the phosphate and the salinity data. And that was very interesting to me. And we looked at it further, and here's the same for the CDOM. So we have a source then of water into the South Fork that's high in CDOM, high in salinity, and high in phosphate. Well, that doesn't fit any of our previous M members. So here's our discharge, and we're looking again through this period now, relatively high discharge and for a relatively long period of time. When we look at it in more detail and further along, so here now we've skipped forward to the 27th of June up past the 4th of July holiday. Now we see very tight correlations between salinity and CDOM. Again, these should be opposite, right? If we're following our general pattern. But here we're very tightly coupled. But then after we get past the holiday, now we see CDOM is maxing out at about 65 to 70 micromolar, or ppb, and the salinity continues to go up. So now we're seeing the influence of the oceanic signal. We're getting salinity moving into the South Fork, but not accompanied with higher CDOM. So that's very different from what we'd seen in the previous week during the high discharge period. So what we think we're seeing then is that there's another source of water to the South Fork. And the most likely source is the North Fork, in which water that's up in the North Fork has got high CDOM, it's relatively brackish, and it's got high phosphate. So now we've got a difference in the dynamic of the estuary, and that changes with the discharge rate. So we saw that relationship between CDOM, salinity, and phosphate change as the flow from Lake Okeechobee changed. So putting that all together, going to the map and looking at our basin relationships, the oceanic water's coming up here, comes into the North Fork, comes into the South Fork. Water flows out through the South Fork into the Middle Estuary, and there is some relationship between the North Fork and the South Fork. And this is sort of our normal period relationship. Pretty much typical estuarine flow. Oceanic waters move in and then flow out on top as a brackish lens. So from the previous, it didn't look like the nutrient dynamics then are driving the system. So let's look at the discharge. Here's the discharge plotted. And again, these are all going to be similar slides as we walk our way through the different sites. So we've got discharge up here, and here's our phosphate values. So SF2, this is coming in from Lake Okeechobee. As the discharge piles up, our phosphate levels actually go down. As we move into the South Fork, we see a nice signal here, and but no great input. But here at the North Fork, up until about the 27th of June, we see a nice tidal signal in the phosphate. And then it decreases and becomes pretty steady through the rest of the time period. So tidal signal going on as the discharge ramps up through this time period, but then hits some critical point, and now we see a much less, both lower phosphate and much less of a tidal signal. And curiously enough, that shows up pretty much at the Middle Estuary too. So if we looked in general, you'd say, oh, the Middle Estuary and the North Fork should have relatively different phosphate values. But in this case, from 27th on, they're very close to the same. And then as we go further on to the ocean, again, on the 27th of June, we lose our tidal signal. So here's our phosphate going up with the tides as the fresh water moves through. But from the 27th of June on, we're not seeing much of a signal at all. And so that's as the bloom really ramped up here. So North Fork, tidal signal through the 27th, and also tidal signal dampening out from the 27th. So what's going on here? Pretty much, I think, in discussions with Dennis and Brian, we're loading the estuary with a lot of fresh water. We're not driving a lot of more nutrients into the system because there's plenty of nutrients already there, and the Lake Okeechobee as a nutrient source isn't particularly rich compared to the sources that are already in the estuary. But what it really is doing is changing the estuarine circulation. And particularly that's true between the North and the South Forks. And what that really means is that we're increasing the residence time of the fresh water in the estuary itself. So we're loading the estuary with lots of water, essentially raising the level in the South Fork, and rather than the flow going back and forth, we've dampened it. And the estuary circulation is all down down near the ocean and up into the middle estuary. We've taken that triple junction at the basins and turned it more into a lake than an estuary. And that's giving time for the blooms to develop within that volume. Well, it turns out Dennis has actually been showing this in a couple of his presentations. This was you were looking at the last year's freshwater input in this one. And then on the next couple of slides comes from early July. I think this is from the discussion you had just a couple of weeks ago that you gave the slides on earlier today. So these are really cool. This is the LOBO plot. So this is just taken from the website. Anybody can go there and do this. So we've got the depth of the sensor and the phosphate. And now we've got correlations, very nice correlations. But this is the South Fork, but there's higher phosphate at high tide. So high tide is when all the ocean water comes in, you would think. But it doesn't get there. We've got higher phosphate at high tide, not at low tide. And interesting enough, at the North Fork, same set of data, same time period, we're getting higher phosphate at low tide. So what's happening is we're piling up the water. It's just sloshing back and forth. At the North Fork station, you're seeing the mix of water that encompasses what we'd seen in the South Fork, the North Fork, and the Middle Estuary sites. So it's moving up the North Fork at high tide, and at low tide it's moving down. The gradient in the phosphate is, of course, positive in the North Fork, so as low tide goes, it's moving down. At the South Fork, it's the opposite. It's lower phosphate towards Lake Okeechobee, so at high tide, it goes low. So you're really now coupling the water within the three basins all together. It's not moving out as fast. I mean, it's still moving out, but you're putting so much more into it from Lake Okeechobee that the system acts much more like a lake. What I really like about this, regards to understanding the actual system, is that three people with very different perspectives approach this data very differently, but we're all pretty much ending up at exactly the same dynamics that we understand the system at. And I was doing it from 3,000 miles away. The next generation, you could be 10,000 miles away. There will be people in Shanghai looking at this data because the web makes difference of 0 from where you are. If you're at your desk, you could be at your desk anywhere to look at that data. That's a really different environment that we're walking into. Okay, so then what do we go back to our slide that looks at the basins? Our high discharge rate, this is the take-home. The oceanic input after a longer period of discharge from Lake Okeechobee. And remember, it didn't happen immediately. It took 7 or 8 days of discharge before this piled up enough to make a difference. But with high input from Lake Okeechobee, we're pushing the oceanic input into just the middle estuary. Very little is coming up into the South Fork or the North Fork. And that lets this area accumulate time. So the phytoplankton that are in there are spending more time. They're not flushing out. We're getting much more of a freshwater system. There's plenty of nutrients here. There's plenty of light in Florida. You get a lot of growth. All right, so summary here. The live data, can I say this too many times? Live data really makes the key to looking at this. And live data gives us a handle that we can actually start impacting what we do when we get that data. It doesn't do us that much good if we're understanding something 2 weeks after it happened. If someone told you, hey, Jimmy Buffett is playing or did play at a bar down the street, that's interesting to you. If they say, hey, Jimmy Buffett's playing now, well, you might be able to get there. But if they say, hey, 2 days from now, Jimmy Buffett's going to be down the street, well, then you can do something about it. Time value of data is really critical in this point. And live data from the LOBOs really makes a huge impact on the ability to manage our resources as we go forward. Okay, that's my soapbox, basically. But what it also is telling us is that discharges from the Lake Okeechobee are really altering the estuarine circulation within the estuary itself. It's not much of an estuary after the Lake Okeechobee input goes on for a while. And that leads to, final point, higher freshwater residence times and excess phosphates leads to the blooms. And let me be clear, this is live data, this is preliminary data, this is what we've been working on. I think the fact that multiple people took a look at the data and we all came to about the same conclusion, that's really good. That means we've got a pretty robust idea. But there's still more work to be done here, lots more work to be done here. And that leads us into what our recommendations are. It'd be very useful to have a fine-scale model of the flow in this area, the juncture of the three basins, relative to the rainfall and discharge. So a nice biogeochemical, physically driven model that looks at the hydraulics of this system and does it and feeds off the real-time data from the LOBO systems would be a great management tool. Within that, then calculate the residence time in the basins as the primary factor in reducing the possibility of further blooms. So, also, we didn't talk about the chlorophyll. We have chlorophyll sensors. We have turbidity sensors. Chlorophyll sensors tell us the particle mass that are plants. Turbidity sensors gives us the particle mass of the total particle mass. But we have phycocyanin fluorometers that do a great job of picking up microcystis. We've got people here who recently came down here who had a site LOBO system off Toledo during the Toledo microcystis bloom that caused them to shut down their water intake. And the phycocyanin fluorometer there worked great to look at that data. Gives us another way of looking at the plant material and also critically to figure out whether it's mycocystis or not. Okay, then we're also recommending LOBO systems at the lake itself. What we really don't know is the changes between the lake and at SF2, and the residence time in the canal is certainly greater than 1 day or two, and of course modulates with flow. That would give us a much better sense of what this input is and the changes along the canal. And then finally, one up in the north to get the what I've called runoff, but it's really other freshwater sources to get data at the top of the basin. So we really have great data in the middle, but we're not getting these two sources well, and a couple of LOBOs would do a great job of doing that. And then finally, in looking at all the data, again, we're surmising this, but we think that if the modulation of the water increases the water outflow, so rather than turning it on and letting it run, if it more looks at the estuarine circulation as to work with it, then we could probably decrease the residence time in the triple juncture and decrease the likelihood in the future of HABs. If the releases have much more of a sinusoidal, tidal type function, and that doesn't necessarily have to happen in a 24-hour. It could happen on days. That might also decrease the residence time and release the fresh water from here. And that's pretty much it.